Okay. There we are. So, tissue perfusion. Perfusion, the term perfusion relates to the amount of blood that goes through a tissue. Does that make sense? Tissue perfusion changes based on the tissue requirements. Oxygen is delivered, carbon dioxide is taken away. Generally, nutrients are delivered. In case of digestive system, nutrients are taken away. Does that make sense? And in case of kidneys, kidneys receive 25% of the blood flow. It's an enormous amount. Quarter of all your blood goes to the kidneys. But kidneys receive it to produce urine, to filter. Okay, good? So perfusion, when we talk about perfusion, we refer to capillaries, right? Capillaries, if you ever saw a river that's like the mountain river, when it goes through its regular bed, which is pretty narrow, right? It goes violently and very fast. But if then it enters some sort of a little valley, or it has a widening of the bed, riverbed, then it slows down. Does that make sense? And then it will accelerate again. So basically, these capillaries, this is the widening of the river, okay? If you would look at the flow rate, you will see that it's the highest in arteries. It's slower in veins, but it's slowest in the capillaries. Makes sense because slow rate allows exchange between the blood and the tissue. Not coincidentally, the slow blood flow, I had no intention to rhyme it, is associated with increased cross-sectional area. Remember we talked about capillaries. Are they wide? They aren't. So each capillary is what, like 7-8 micrometers in diameter. But there are so many of them, then the total area of all capillaries is enormous. Do you understand what I'm saying? Okay? That's why the blood flow can be slow. Does that make sense? Okay? So what can regulate tissue perfusion? There are metabolic controls and myogenic controls, right? Before we move any further, I want you to understand one very clear distinction between the local and systemic controls. It's really important. So we have systemic control of cardiovascular system, right? What is the most important systemic parameter, measurable systemic parameter in cardiovascular system? We can measure it. Blood pressure. So cardiovascular system, in terms of homeostasis, tries to maintain blood pressure constant. Does that make sense? On the local level, though, the most important thing is the tissue perfusion. Does that make sense? So you have to understand that local controls may not go sort of hand in hand with the systemic controls, and local changes may not really affect systemic picture. Do you understand what I'm saying? So say if blood pressure is, so imagine you have a like regular, like me, okay, regular person. Okay, my blood pressure is at a certain level now, all right? So which means my peripheral resistance is rather the same. We good? That makes sense? Which means blood flow is the same. Systemic blood flow is the same. That makes sense? Now, if I have eaten an egg just like 10 minutes ago, so there is some digestive activity going on. What's going to happen to the blood flow to intestine, to the stomach? It's going to increase. Is it going to affect my systemic blood flow? Probably not. It's going to increase at the expense of other organs. Does that make sense? So this is something that you have to keep in mind. Local tissue perfusion, tissue needs. That's the most important part. Okay? How can you control it? You can change the diameter of small arteries. You can change the diameter of arterioles. And they can respond to the metabolic changes or the changes in the smooth muscle activity. Metabolic changes. What is the purpose of the blood flow to the tissues? Tell me now. Okay, deliver nutrients. What else? Deliver oxygen. What else? Huh? Remove waste. Very good. And remove CO2. Now, without even looking there, let's see what's going on. If your tissue is very metabolically active, the easiest way, honestly, muscle. Let's do muscle. So if muscle is metabolically active, in terms of nutrients, does it need more or less? More. In terms of oxygen, more. In terms of CO2 production, it produces more CO2, which means what do you have to do with that CO2? Take it away. Does that make sense? So if you need to deliver more nutrients, more oxygen, and take away more CO2, what do you need to do? What do you need to do with the blood flow? You need to increase it. Does that make sense? So basically, metabolically active tissues, right here, they will increase their own perfusion. Okay? How can you increase the amount of blood locally that reaches the tissue? There's only one way. Vasodilation, period. Does that make sense? It's a local change. We got it? So, tell me now, I'm gonna give you like a parameter, and you're gonna tell me what change of this parameter will cause vasodilation. CO2 in the tissue needs to go up or down? Up to cause vasodilation. Does that make sense? Oxygen in the tissue has to go down to cause vasodilation. pH in the tissue has to go down to cause vasodilation so that acid will be removed. ADP in the tissue. What is when ADP is generated? When ADP is produced in the tissue. Which reaction produces ADP? No. ADP, adenosine diphosphate. When is it produced? When ATP is broken down to release energy. Metabolically active tissues use a lot of ATP, right? Produce a lot of ADP. Accumulation of ADP will cause what? Vasodilation. Does that make sense? Also, it turns out inflammation and metabolic activity, they're very similar. There are molecules called prostaglandins. I love them. Prostaglandins, they will also increase blood flow. Now, it's not really digression, but to give you a clinical connection. When somebody has an injury to the tissue, it causes inflammation. One of the signs of inflammation is hyperemia, redness of the tissue. In Latin, it's called rubor, right? Increased blood flow to the site of the injury. Reasons: one, remove all the wastes and all the crap. Two, to bring white blood cells that will take care of the debris and dead cells and whatever damage there is. Does that make sense? Prostaglandins, they mediate that inflammation. They control the inflammation. They control the blood flow. That makes sense. Actually, the mechanism is fascinating. What dilates blood vessels? Which tissue is controlling the diameter? Smooth muscle, right. But turns out that endothelial cells first have to produce nitric oxide. Nitric oxide, which then acts on smooth muscle cells and dilates the blood vessels. Okay? One of the drugs that is used to treat various vascular pathologies, cardiovascular disease in general, endothelial dysfunction, is cysteine. You may have heard about it. It's pretty much amino acid. Cysteine is a source of nitric oxide. More famous source of nitric oxide is Viagra. It induces nitric oxide production in endothelial cells, which act on smooth muscle cells and dilate blood vessels. Basically, you can prescribe Viagra as the acute anti-hypertensive treatment. Okay, it's going to be off-label prescription, but that's what this drug was initially developed for, as the anti-hypertensive drug. Do you understand the idea of metabolic controls? So elevated CO2, lowered pH or acidosis, lowered oxygen, ADP, inflammatory mediators will all cause vasodilation. Does that make sense? And if you flip those parameters, it will be the opposite. Does that make sense? Okay. Myogenic. When blood vessel stretches, it responds with a constriction. That's it. Does that make sense? And when stretch is relieved, say, imagine now, how does it work? Think about this. If blood pressure, that's a great example. Blood pressure goes up, systemic blood pressure goes up. What happens to the systemic blood flow? Increases, of course. If systemic blood flow increases, Lexi, maybe you will tell me, what happens to the blood flow through each separate organ? Of course, it increases because it increased all across the board. Does that make sense? Is it good? Great. It depends. Think about this. Those capillaries are fragile. So if suddenly there is a spike in the blood pressure, it may damage the capillaries. So local organs will try to kind of stop that from happening, okay? When those little tiny arterioles will stretch in response to the spike of the blood pressure. If that increased perfusion is not necessary, they're going to respond by contracting and limiting blood flow to the capillaries downstream. Does that make sense? Okay? And vice versa, if blood pressure drops, say blood pressure decreases, you need to maintain the pretty standard blood flow, let's say, to the heart. Does that make sense? blood pressure decreases, coronary arteries will start to dilate to maintain, to increase the blood flow to the cardiac muscle. Does that make sense? Okay? That's myogenic. In response to increased stretch, muscles constrict. Contract in response to decreased stretch, they relax and blood vessel dilates. That makes sense. We talked about neuronal and hormonal regulation. Just want to remind you that atrial natriuretic peptide is vasodilator. Epinephrine, norepinephrine, angiotensin, and ADH are vasoconstrictors. Okay. Long-term regulation. Angiogenesis. When people grow, blood pressure increases. Does that make sense? Like if the tissue grows, then the system of the blood vessels that is in place doesn't match the requirements. Like when the city grows, you have to build new roads. Does that make sense? I'm the witness of what happens if you build new buildings without building new roads. In my hometown, we had a little neighborhood of private houses, like suburban houses, and they bought it out, demolished all the houses, and built the huge apartment complexes, like 18 stories. So instead of, say, 200 people at the same place, there were like 5,000 people living in the same area. And driving through that, it's just dead end. I walk faster than the cars go in that morning traffic. It's terrible. Because the road is still the same. They didn't build anything new. So this is actually leads us to a very interesting point about cancer. When tumor grows, its core is often necrotic. Any idea why? Yeah, lack of blood flow. It grows so fast that blood vessels, they just don't have time to deliver nutrients. The cells just die. But cancerous cells, they usually produce chemicals, so-called angiogenic factors, that stimulate the growth of blood vessels. Do I make sense? So they can grow. Well, guess what? There are drugs on the market now that inhibit angiogenic factors in the tumors and basically suffocate the tumors. I mean, they're not ideal, but they shrink the tumors, basically. Does that make sense? Anti-angiogenic drugs. Now, blood flow to specific organs. I'm going to be sort of restrictive here. First, muscles. So, 1 liter per minute at rest, 12 liters per minute during exercise. Vasodilation. And the regulation in the muscle is metabolic. Muscles produce enormous amount of CO2. Does that make sense? So that's mainly metabolic control. Does that make sense? Brain is absolutely fascinating. So brain shows so-called autoregulation in the certain range of blood pressure. Let me explain what's going on. Imagine that blood pressure, your blood pressure starts to rise from normal. What happens to initially to the amount of blood that gets to the brain? Goes up. What happens to the pressure in the capillaries in the brain? Goes up. And what would happen to the capillaries if that would be true? They would start to leak. And we would have brain edema and we would die. Does that make sense? So what happens? It's myogenic control here. okay? High blood pressure increases the stretch of the arterioles. Does that make sense? What happens to them? They constrict. In response to elevated blood pressure, they constrict and they limit the amount of blood that goes to the brain. Does that make sense? If blood pressure drops in response to reduced stretch, those arterioles will dilate, maintaining basically the amount of blood at the same level. So in that range, between about 50 to 150 millimeters of mercury, blood flow to the brain remains constant. That makes sense? Now, what if you go below that? If you go below 50, myogenic controls cannot maintain it anymore. They cannot vasodilate anymore. And they will just simply, become less and less stretched due to the low blood pressure. Blood flow will decline and the person will faint. Okay? If blood pressure goes above 150, what's going to happen? They cannot constrict anymore. They practically give up, start to dilate in response to increased blood pressure. Blood rushes into the capillaries, damages them, brain edema. Does that make sense? But autoregulation is very neat. We're good about it. Metabolic regulation. Is it included? Yes. Think about this. When you think, what's going on in your brain? Neurons, what do they do? Huh? So again? They conduct electrical impulses. Between the neurons at the synapse, what do they release? Neurotransmitters. Do they make them themselves? Yes, they do. They constantly churning out those neurotransmitters. They transport them. They take them back. They spend enormous amount of energy on all of this. And they spend it in the form of ATP, right? So it's constant aerobic respiration. So when you listen to me now, your Wernicke's area, which is right here and right here, Wernicke's area gets activated. That makes sense? Because you understand the spoken words. It's activated, so it consumes a lot of oxygen, right? To produce ATP and so on and so forth. So what about CO2 amount in that particular area? It's constantly produced. So what you need to do with that CO2? You need to get rid of it, so that local area will be perfused more. Does that make sense? So metabolic regulations in the brain are equally important. Skin is disposable, so controlled by sympathetic system. If you need to vasoconstrict something to save the blood for something else, that's going to be skin. That's why when people lose blood, they pale. Blood flow to the skin becomes limited. And yeah, in sympathetic stimulation, it's kind of interesting. I don't want to go there too much, but it depends on what person produces more, norepinephrine or epinephrine. If in response to the stress, you produce norepinephrine, then skin blood vessels become constricted, and you frightened, you pale. But if you produce more epinephrine, then skin blood vessels are dilated. Well, people, when they're angry, they're red. That's epinephrine plays. There's some really nice story about it, but just time-wise, we're not going to talk about it. So basically, the main regulation of the skin blood vessels actually is nervous by a hypothalamus. Temperature regulation mostly. Lungs. I'm talking pulmonary circuit now. Remember, pulmonary circuit. So in pulmonary circuit, blood gets to the lungs. What does it pick up there? Oxygen. Do you want blood to go to the areas with more oxygen or less oxygen? More. So unlike in tissues, in pulmonary circulation, areas of lungs that are oxygen saturated are perfused better. Do I make sense? So it's opposite, only for the pulmonary circulation. Does that make sense? It's called ventilation perfusion coupling. The areas of lungs that are ventilated the best have the most blood flow because blood picks up oxygen. That makes sense? Heart. With heart, the problem is that coronary vessels are squeezed every time the heart contracts. So blood flow happens only during diastole, really. Okay. Mainly myogenic control, as I mentioned. If blood flow decreases, then vessels dilate to maintain the blood pressure decreases, vessels dilate to maintain the blood flow to the heart. Does that make sense? That's pretty what we just discussed, myogenic versus metabolic control. So at rest, it's mostly myogenic. When you start exercising, your blood produces a lot of CO2 and metabolic controls take over. Okay? Now, we're going to chat now about the fluid exchange. And what I want to we talked about different types of capillaries, right? Continuous, fenestrated, and sinusoid. What you have to understand that in capillaries, there's an exchange of respiratory gases, oxygen, CO2, right? There's an exchange of nutrients. There's also an exchange of fluids. Fluid, and I specifically say fluid. I don't want to say water, because it's more than water, it's fluid, okay? Fluid leaves capillaries and goes back into them. And I'm going to make a very strong statement, which I'm going to prove to you, that fluid leaves capillaries and goes into the tissues on the arterial end and comes back to capillaries on the venular end. Does that make sense so far? Okay, there is a flow out and back. Okay? Now, imagine that you have a membrane, a filter, of sorts. How would you drive the fluid through the filter, through the membrane? What do you need to apply to a fluid? Pressure. Transport of fluids across the capillary wall is guided by pressure. Does that make sense? First, we're going to talk about hydrostatic pressure. And think about if you have a hose, garden hose, with a fluid in it, and you start poking holes. What's going to happen through those holes? Little leakage, right? That's hydrostatic pressure of the water in the hose. Does that make sense? So basically, hydrostatic pressure is the mechanical pressure of fluid, and I always say hydrostatic pressure pushes. Does that make sense? Capillary hydrostatic pressure. It's the pressure of blood inside of the capillary. Do I make sense? Pressure of blood inside the capillary. Where does it push fluid to? Say again? Perfect, to the tissues. From the capillary to the tissues. Do I make sense? technically, there is a interstitial hydrostatic pressure. Pressure that is exerted, quote unquote, by the fluid in the tissue. Do I make sense? Where does it push fluid to? Interstitial hydrostatic pressure. Where does it push the fluid? Vessels. Back in the vessels. Does that make sense? Interstitial hydrostatic pressure is 0. You know why? Lymphatic system. Normally, all excessive fluid in the tissues immediately drains into the lymphatics. Does that make sense? Do you get hydrostatic pressures? So capillary pushes the fluid from the capillaries into the tissue. Interstitial pushes it back. Osmotic pressure. This pressure is exerted by proteins. They're solutes, right? Okay, that makes sense? They're solutes. So proteins that are in the blood, albumin, okay, that protein in the blood called albumin, it will attract water. Now, if albumin is in the blood, it's going to pull the water where? From the tissue into the vessels. This is called capillary osmotic pressure. Does that make sense? Capillary osmotic pressure pulls the fluid back into the blood. Do I make sense? Now, there is a little bit of protein in the interstitial space in the tissue. So capillary interstitial fluid osmotic pressure will pull the fluid in the tissue. Does that make sense? Now, arterial end. So this is hydrostatic pressure, pretty much a blood pressure. Where does the fluid go? For this tissue, for this pressure. Where does it push it? Into the tissue. The thick blue arrow. Can you see that? This one. So 35 millimeters. Capillary osmotic pressure. Where does it pull fluid? From back, right? So they work against each other. So 35 drives to the right, 26 drives back. What's the difference? What a shame. 9. Okay, 9. Hydrostatic pressure from the tissue, is there any? None, so we can disregard that 0. And there is capillary pressure, osmotic pressure from the tissue that pulls the fluid into the tissue, and it's 1 millimeter. So net pressure, net flow will be what? 10. That makes sense. 10 millimeters. And at arterial end, you can see that this pressure will drive fluid into the tissue. Does that make sense? We good? We're gonna play with some things here in a little bit. Venous end. What is the difference between arterial end of capillary and venous end of capillary? The only one difference. Yeah, but in relation to pressures, which pressure is going to be different? Yes, hydrostatic pressure on the arterial end is going to be higher than hydrostatic pressure on the venular end. Does that make sense? Because you have a gradient of pressures. We good? Everything else is going to be the same. Protein concentrations are the same. There's no hydrostatic pressure in the tissues. So let's take a look here. Hydrostatic capillary pressure, 17, right? Osmotic capillary pressure is still 26. It's the same blood. So what's the resulting difference? 26 minus 17. Really? You want me? 9. These 9, where are they directed? These 9 are directed towards the capillary, right? And there's this little osmotic pressure from the tissue that takes 1 out of 9. Does that make sense? Because it's in opposite direction. So what's the resulting so-called net filtration pressure? 8. What was net filtration pressure at the arterial end? 10. Here's 8. What does that mean? Yeah. Which means it loses what? If it loses pressure, it loses fluid. It loses fluid. Does that make sense? It means that not everything that leaves on the arterial end comes back at the venular end. The difference, where does it go? What would happen if, does it stay there? Where does it go from the tissues? Lymphatic system, the sewage. What's the point of it? What's the point of that flow? What's the point of that fluid flow through the tissues? Do you like Greek mythology? Hercules, well, technically Hercules is Roman, but you know what I'm talking about. Hercules, he had like 12, whatever, achievements, how you call it, I don't know. So in one of the tasks that he had to do, had to clean up the stables of one king. And what he did, he directed rivers into those humongous stables and they washed away all the crap. This 2 millimeters of mercury that you lose in the tissues, that flow, essentially washes away all the crap from the tissues into the lymphatic system. Does that make sense? Let's play a little bit with these parameters. What happens if your blood pressure increases and so if blood pressure increases, which parameter is going to change? Which of these 4 pressures is going to change only? Capillary hydrostatic. If it goes up, say 1 millimeter of mercury and becomes 36 instead of 35, what's going to be the net filtration pressure at the arterial end? Instead of 10? 11. Yeah, 11. It's fine. What's going to be the net filtration pressure here? Instead of 8? 7. Because the opposite way, right? What's the difference between 11 and 7? 4. It's 4. Okay, I didn't hear that. 4. Now, normally, what's the difference? 2 between 10 and 8. Now, I didn't hear that either. So, normally it's 2, now it's 4. What does that mean in terms of the fluid motion? More fluid goes into where? Tissue. Oh, lymphatic can absorb only so much, right? Does that make sense? So more fluid goes into the tissues. Tissues become edematous. If you stay for an extended period of time, your capillary pressure in your legs is going to increase. People who stand they often experience swollen ankles, swollen feet. Does that make sense? How do you treat it? How do you treat swelling? What do you put on your feet? Huh? Compression socks. So what do they do to the tissues? I like that. They compress it, exactly. Which parameter they increase? They basically turn it from 0 to more than 0. Tissue hydrostatic pressure. Does that make sense? Okay? Good? Now, playing with another. What if you will increase somehow the concentration of albumin in the blood? Say you are severely dehydrated. So the concentration of albumin in the blood goes up. Which pressure will change? Osmotic. Which osmotic? Capillary, right? Osmotic capillary pressure. How is it going to change? If albumin in the capillaries goes up, it's going to increase as well. More fluid is going to be pulled into the blood. So if 26 goes from 20, if osmotic capillary pressure, this one, goes from 26 to say 27, what's going to happen to net filtration pressure? It's going to go from 10 to 9. If it goes from 26 to 27, this is going to go from 8 to 9, just in opposite way. So what does that mean for the tissue? If 9 is on one end, goes into the tissue, and 9 on another goes out. No extra fluid in the tissues. Does that make sense? Which means dehydration. Last thing. Some people, some women that undergo mastectomy, severe mastectomy, radical mastectomy, okay? Not lumpectomy, not moderate mastectomy, but radical mastectomy. They also sometimes have the lymph nodes and lymphatic vessels removed. And especially if, say, a woman undergoes right side radical mastectomy, she often has a characteristic symptom on the right side. They have massive swelling in the right arm because the drainage of the fluid that normally accumulates in the tissue and should be drained in the lymphatic system, drainage of the fluid is severely impaired. Does that make sense? The treatment, not treatment, but sort of a, well, you can say treatment management thing. Have you seen ever? Special sleeves, compression sleeves, they put on the arm, so at least it pushes some of it in the remaining lymphatic vessels. Pushes back in the blood. That makes sense. What I want you to very clearly understand about this tissue exchange. These are questions that are logical, but you have to have a very clear understanding what's going on. You must be able to tell me, like, proteins in the capillaries exert capillary osmotic pressure. Okay. If you increase blood pressure, this pressure will go up, capillary hydrostatic. If you decrease blood pressure, this pressure will go down. Okay. If you obstruct lymphatic vessels, this pressure will go up, interstitial hydrostatic. If you will increase the concentration of proteins in the blood, capillary osmotic pressure will increase. And you have to understand, if we increase, say, capillary osmotic pressure, what happens on the arterial end? What happens on the venular end? Does that make sense? Okay, good? Okay. Exam, next Monday. 50 questions, only physiology. We're going to do the review this Wednesday. Deal?